There's a machine sitting inside a handful of buildings on Earth that decides who gets to build the future. It is not a computer, though it makes every computer possible. It is not a weapon, though nations have gone to war footing over who is allowed to buy it. It is a lithography machine, built by a single Dutch company, and for 20 years, nobody has been able to touch it. Every phone in your pocket, every AI chip training the next generation of large language models, every satellite, every missile guidance system, every piece of modern military hardware traces its existence back to this one company and the machines it builds. The company is ASML, and for the first time in a generation, there's a serious government-funded multi-hundred-million-dollar bet that its monopoly might not last forever. This is the story of that bet. It involves a fired Intel CEO trying to rebuild his legacy, a particle accelerator the size of a football field, a wavelength of light so short that scientists once thought it was physically impossible to generate reliably, and a scramble by the American government to buy its way out of dependence on a single foreign supplier. Some headlines call it quantum technology. It is not quantum technology, not in the way you're probably thinking of quantum computers with qubits and superposition, but what it actually is might be even stranger, and the stakes are just as high. To understand why this matters, you first have to understand what ASML actually does, because most people who have heard the name have no real sense of the scale of what these machines accomplish. Modern chips are built by printing patterns onto silicon wafers using light. You design the layout of a chip, transfer that design onto a stencil-like mask, and then shine light through the mask so it hits a photosensitive chemical layer on the wafer. Wherever the light hits, the chemistry changes, and that change becomes the blueprint for the transistors that get etched into the silicon. This has been the basic idea behind chip making since the 1960s. The problem is that transistors have gotten so small that ordinary visible light is now far too wide, far too clumsy, to draw the necessary detail. Trying to print a modern chip with visible light would be like trying to write a sentence with a paintbrush the size of a broom. The solution the industry landed on decades ago was to use shorter and shorter wavelengths of light, because shorter wavelengths can draw finer detail. Chipmakers moved from visible light to ultraviolet, then to deep ultraviolet, squeezing every bit of precision they could out of that approach for years. But eventually deep ultraviolet hit its own wall too. The transistors the industry wanted to build were simply smaller than what that light could reliably print. The answer, first proposed decades ago and considered by many physicists to be borderline impossible to commercialize, was extreme ultraviolet light, a wavelength of about 13.5 nanometers. That is roughly 1/10,000th the width of a human hair. At that wavelength, ordinary lenses do not even work anymore because the light gets absorbed by almost everything, including air. You cannot use glass lenses. You have to use mirrors so precisely polished that if you scaled one up to the size of Germany, the tallest bump on its surface would only be a few centimeters high. You have to do all of this inside a vacuum chamber because the extreme ultraviolet light would simply be swallowed by regular air. Generating that light in the first place is its own miracle of engineering. ASML's approach works like this. A tiny droplet of molten tin, smaller than the head of a pin, is shot through a vacuum chamber at incredible speed. A high-powered carbon dioxide laser strikes that droplet, first with a small pre-pulse to flatten it into a disk, and then with a much more powerful second pulse that vaporizes it into a plasma so hot it reaches temperatures around 500,000 degrees Celsius, hotter than the surface of the sun. That superheated plasma emits extreme ultraviolet light as a byproduct. This happens 50,000 times every single second, with a laser hitting a microscopic droplet of tin with such precision that engineers have compared the accuracy required to hitting a coin from a mile away, every single time, without fail, for hours on end. It took ASML and its partners the better part of 2 decades and tens of billions of dollars in cumulative investment to make this process reliable enough to sell as a commercial product. Multiple times, the whole approach nearly got abandoned. Competing companies gave up. ASML did not, and eventually it built the only machine on the planet capable of doing this at industrial scale. The result of that 2-decade slog is a machine roughly the size of a bus, containing more than 100,000 precision parts, weighing around 200 tons, and costing somewhere in the range of $200 to $400 million per unit, depending on configuration. Every single one of these machines that exist in the world today was built by ASML. Not most of them, all of them. There is no second source. If you are Intel, if you are TSMC, if you are Samsung, and you want to manufacture the most advanced chips on the planet, you have exactly one company you can call, and that company sets the price, sets the delivery schedule, and effectively decides how fast the entire semiconductor industry is allowed to move forward. This is not a small detail buried in an annual report. It is arguably the single most consequential monopoly in the modern global economy. Every leap forward in artificial intelligence over the last several years has depended on chips that could only be manufactured because ASML's machines exist. The GPUs powering the largest AI models on the planet, the custom silicon inside your phone, the processors running data centers around the world, all of it traces back through a supply chain that has exactly one choke point. And because of that choke point, ASML has become one of the most geopolitically sensitive companies on Earth. The United States has pressured the Dutch government for years to block the export of ASML's most advanced machines to China, specifically to slow down China's ability to build cutting-edge chips for artificial intelligence and military applications. Those export restrictions have held mostly, though there have been controversies, including reports of ASML selling older deep ultraviolet equipment and components to Chinese firms with ties to military and quantum research institutes, which triggered fresh political fallout in the Netherlands and renewed scrutiny in Washington. So when you have a single company controlling the physical bottleneck for the most important technology of the century, and when access to that company's machines has become a literal instrument of international policy, it becomes obvious why any credible attempt to build an alternative would attract enormous attention, enormous money, and enormous hype. That is exactly what is happening right now with a company called XLight. XLight is a startup based in California, founded a few years ago, that spent most of its early life working quietly, almost invisibly, on a very specific and very difficult problem. It was not trying to build a whole new lithography machine from scratch. That would be an almost impossible task for a startup, given that ASML's advantage is not just one invention, but literally thousands of interlocking innovations built up over decades, protected by patents, refined through relationships with suppliers, and battle-tested across a global customer base. Instead, XLight picked one component of the puzzle. Not the mirrors, not the vacuum chambers, not the wafer stages, the light source itself, the part of the machine that actually generates the extreme ultraviolet light in the first place. Here is where the story gets its dramatic pull. XLight's approach does not use molten tin and a carbon dioxide laser at all. It uses something borrowed from particle physics, a free electron laser powered by a compact linear particle accelerator. Instead of vaporizing tin droplets, XLight's system fires electrons down a roughly 25-meter accelerator, pushing them to nearly the speed of light, then manipulates their path through a series of magnets, so that as they wiggle back and forth, they emit extremely precise, extremely tunable light. In theory, this approach can be pushed to wavelengths as short as 2 nanometers, dramatically shorter than ASML's current 13.5 nanometer standard. It can also, at least according to XLight's own claims, generate significantly more power than the plasma method, be tuned to different wavelengths depending on what a chipmaker needs, and be built as a shared, centralized facility that feeds light to many lithography machines at once instead of requiring every single scanner to generate its own light internally. If you are picturing something like the particle accelerators used at facilities such as CERN, you are on the right track, just at a dramatically smaller and more industrial scale. This is not science fiction. Free electron lasers already exist and are used in research facilities around the world for various forms of advanced physics and materials research. What XLight is trying to do is take that underlying technology, which has mostly lived in national laboratories and university research centers, and shrink it, harden it, and industrialize it to the point where it can sit next to a chip fab and reliably feed light into commercial lithography tools, 24 hours a day, for years at a time, without the kind of downtime that would bankrupt a semiconductor manufacturer. The person who put this company on the map, at least in terms of public attention, is Pat Gelsinger. If that name sounds familiar, it is because Gelsinger spent decades at Intel, left, came back years later as CEO to try to turn the company around, and was then pushed out by Intel's board after a stretch of weak financial performance and repeated delays in the company's manufacturing roadmap. For a lot of people who followed the semiconductor industry closely, Gelsinger's departure from Intel looked like the end of a chapter. Instead, it turned out to be the beginning of a new one. Not long after leaving Intel, Gelsinger joined the venture capital firm Playground Global as a general partner, and it was through that firm that he first connected with XLight. Playground Global had already invested in the company as part of an early funding round. Gelsinger did not just write a check, though. He joined XLight directly as executive chairman of the board, lending the startup something that no amount of venture capital alone can buy: instant credibility with the exact customers it would eventually need to sell to. When the former CEO of Intel, a man who spent 2 decades making purchasing decisions for one of ASML's largest customers, stands up and says a new light source technology could reshape the industry, chipmakers listen differently than they would to an unknown founder with a compelling slide deck. The technical leadership at XLight comes from a different world entirely. The company's CEO, Nicholas Keeles, built his career not in semiconductor manufacturing, but in quantum computing research in government laboratories, which is very likely the real source of the confusion behind headlines, calling this a quantum machine. The technology itself is not quantum computing. It has nothing to do with qubits or superposition or entanglement, but the people building it come out of a research culture adjacent to quantum computing, working with the kind of exotic, high-precision physics equipment that quantum labs rely on every day. It is an understandable mix-up, and frankly, a useful one for headline writers. But it is worth being precise about, because conflating this with quantum computing hides what is actually interesting about the story, which is that a completely different physical process, borrowed from particle accelerator research, might be able to outcompete ASML's decades of refined chemistry and optics. For years, XLight worked mostly outside the spotlight, developing its technology in relative obscurity while the broader industry focused on GPUs, AI training clusters, and the endless race for more compute. That changed abruptly at the end of last year, when XLight quietly connected with officials in the Trump administration. According to Gelsinger's own account, he pitched Commerce Secretary Howard Lutnick on the idea of backing XLight even before Lutnick had been formally confirmed for the role, positioning it as a way to reclaim American leadership over a critical piece of the chip-making supply chain that has, for the past 2 decades, belonged entirely to a company in the Netherlands. The pitch apparently landed. In December, the Department of Commerce, working through the National Institute of Standards and Technology's CHIPS Research and Development Office, signed a non-binding letter of intent to provide up to $150 million in federal incentives to XLight under the CHIPS and Science Act. In exchange, the government would receive an equity stake in the company, continuing a pattern the administration has followed elsewhere, including its earlier multi-billion-dollar equity stake in Intel itself. Commerce Secretary Lutnick framed the funding in explicitly nationalistic terms, saying that America had ceded the frontier of advanced lithography to others for far too long, and that under this administration, those days were over. That government backing was not the end of the fundraising story. It was closer to the beginning of a much bigger one. Around the same time, reports emerged that XLight was in active talks to raise as much as $350 million in a new private funding round, with major investment firms including Boardman Bay Capital Management and Bain Capital positioning themselves to lead it. What makes this round particularly striking is who else is reportedly circling it. According to multiple reports, the list of parties expressing interest in participating includes not just financial investors, but actual semiconductor companies, among them TSMC, Intel, Micron, and, in what might be the most surprising detail of the entire saga, ASML itself. Think about what that means for a moment. The company whose monopoly is theoretically being threatened is reportedly among the parties interested in investing in the startup trying to challenge it. That is not necessarily as contradictory as it sounds, and we will get to why in a moment, but it is a detail that completely undercuts the simplistic version of the story where a scrappy underdog is racing to slay a corporate giant. The reality is far more layered than that. Combine the CHIPS Act commitment, the earlier venture funding, and this new round, and XLight is looking at somewhere in the neighborhood of $550 million in total capital raised or committed, an enormous sum for a company that has not yet produced a single commercial product. The plan, as laid out publicly, is to build a prototype free electron laser system at the Albany Nanotech Complex in New York, a facility already established as a hub for advanced lithography research, and to target producing its first silicon wafers using the new light source by 2028. That is not tomorrow. That is not next year. That is years away, and in an industry where technology roadmaps slip constantly, even that 2028 target should be treated as an optimistic best case rather than a locked-in certainty. Now here is where the story needs a serious dose of reality, because the version of events implied by headlines like "the machine that could make ASML obsolete" is, frankly, misleading. XLight is not building a competing lithography machine. It is not trying to build the 200-ton scanner, the vacuum chambers, the mirror systems, the wafer stages, or the software stack that actually positions a silicon wafer with atomic-level precision under a beam of light. Those pieces represent decades of accumulated engineering knowledge that ASML has built up through its own research and through partnerships with an enormous ecosystem of specialized suppliers. XLight is focused on exactly one component, the light source. Its own public materials make this explicit. The pitch is not replace ASML. The pitch is feed a better, cheaper, more efficient light source into the machines ASML already builds, and eventually into next-generation systems as well. In fact, XLight has stated that a single one of its free electron laser installations could theoretically support as many as 20 separate ASML lithography scanners simultaneously, acting as a shared utility rather than a self-contained replacement for the entire machine. that reframes the entire narrative. This is not, at least not yet, an insurgent startup racing to overthrow a monopoly. It is closer to a company trying to become an upgrade path, a supplier of a critical subsystem that could make ASML's own machines more powerful, more efficient, and cheaper to operate. If XLight succeeds, the most likely outcome in the near term is not that ASML gets replaced. It is that ASML's machines get better, running on a new kind of light source that could, according to XLight's own figures, deliver up to 4 times the power of today's plasma-based systems, cut wafer processing costs by something in the range of 30 to 50%, and dramatically reduce the energy consumption per chip produced. Multiple industry analysts have made exactly this point directly. The framing that matters is not overnight apocalypse for ASML. It is a wake-up call, a new competitive pressure injected into a market that has effectively never experienced any pressure at all, because there has never been a credible alternative before. And that is precisely why this story matters, even if XLight never ships a single commercial unit. Analysts covering the space have made an important observation. It is not actually necessary for XLight to succeed in order to change behavior across the entire industry. It is only necessary for XLight's approach to be credible enough that chipmakers, investors, and governments start planning around the possibility that it might work. The moment a credible alternative light source exists on paper, ASML's negotiating leverage over pricing, delivery timelines, and feature roadmaps shifts, even slightly. Every major chipmaker evaluating billions of dollars in future capital expenditure has to at least consider the scenario where a fundamentally different physical approach delivers dramatically more power, dramatically better energy efficiency, and tunable wavelengths reaching all the way down to 2 nanometers. That kind of possibility, even years away from being proven, changes the calculus of an entire industry's long-term planning. There's also a deeper, more structural reason the American government is willing to put public money behind a long-shot bet like this one. ASML is not just a company, it is a single point of failure sitting at the center of the entire global technology supply chain, and it is headquartered in a country that, while a close ally of the United States, is still a separate sovereign nation with its own interests, its own politics, and its own vulnerability to pressure from other governments, including China. For years, Washington has leaned on the Dutch government to restrict ASML's exports to China, and for the most part, that pressure has worked. But it has also exposed just how much of America's own technological future depends on decisions made in another country's capital about a company America does not control. Funding XLight is best understood as a hedge against that dependency. Even a partial, years away, unproven alternative light source changes the strategic calculus because it establishes the possibility of an American-controlled node inside a supply chain that has, until now, had exactly one irreplaceable link, and that link was foreign. It is worth pointing out that XLight is not the only company chasing this opportunity, and looking at the wider field helps put its odds in better context. A separate company called Substrate, based in San Francisco and backed by investor Peter Thiel, has developed its own chip-making system that it claims can rival ASML's most advanced lithography machines, using a completely different method built around a particle accelerator, generating light from shorter wavelength X-rays, aiming for even narrower and more precise beams than either ASML's current approach or XLight's free electron laser concept. Meanwhile, on the other side of the Atlantic, a Dutch startup called Euclid is chasing a different but related opportunity, not lithography itself, but AI inference chip design, aiming to compete with NVIDIA rather than ASML. What makes Euclid notable in this same conversation is its bloodline. The company is advised and backed by Peter Wennink, the former chief executive of ASML himself and was founded by another ASML alumnus. When you step back and look at the whole picture, what you see is not one lone challenger taking on a monopoly, but an entire wave of deep tech investment flowing back into the unglamorous hardware layers underneath the AI boom, lithography, chip inspection, metrology, advanced packaging, memory, and interconnects, categories that spent years being treated as boring, commoditized infrastructure, and are now attracting serious capital because everyone has realized that without them, none of the flashy AI applications sitting on top would be possible at all. There's also a China dimension to this story that cannot be ignored, even though it runs on a separate track from XLight specifically. Chinese firms, cut off from ASML's most advanced EUV machines by export controls, have been racing to find workarounds using older deep ultraviolet technology and entirely new manufacturing approaches. There have been reports of Chinese chipmakers achieving advanced process nodes without EUV tools at all, relying instead on more complex, more expensive multi-patterning techniques using older equipment and separate reports of prototype domestic EUV lithography machines undergoing early testing inside China. None of this changes the fundamental physics challenge that made EUV so difficult to build in the first place. And most independent analysts remain skeptical that China can close that gap quickly. But it does mean that ASML's monopoly is facing pressure from more than one direction at once, from American-funded startups trying to out-innovate it, and from a determined geopolitical rival trying to rout around it entirely. So, where does that leave ASML itself in all of this? Surprisingly calm, at least publicly. ASML's own leadership has acknowledged that the global semiconductor market remains tight, with demand from artificial intelligence, satellites, and robotics all outpacing what the industry can currently produce. And the company continues to project meaningful growth even as uncertainty clouds the outlook further out. Rather than treating XLight purely as a threat, ASML appears to be at least keeping the door open to some form of collaboration, which lines up with reports that the company may participate in XLight's upcoming funding round. If that participation happens, it would tell you almost everything you need to know about how ASML actually views this technology, not as an existential threat to be crushed, but as a potentially useful upgrade to its own product line, something it might rather help build and eventually integrate than watch develop entirely outside its control. There is a version of the next decade where XLight succeeds spectacularly, and the headline is not ASML destroyed, but ASML's machines just got 4 times more powerful, thanks to a light source it eventually decided to buy into. None of this should be read as certainty that XLight will succeed at all. This is still, fundamentally, an unproven technology attempting an extraordinarily difficult engineering task, shrinking and industrializing physics that has mostly lived inside research laboratories, and doing it reliably enough to run inside a commercial chip fab, where downtime costs manufacturers staggering amounts of money every single hour. ASML did not build its current monopoly by accident. It took the company and its partners roughly 2 decades and tens of billions of dollars in cumulative investment just to make plasma-based EUV work reliably at commercial scale. And even now, scaling that plasma approach beyond roughly a kilowatt of output power runs into serious physical limitations, including debris from vaporized tin contaminating the delicate mirror systems inside the machine. If a company with ASML's resources, timeline, and singular focus needed 20 years to get its approach working, there is no guarantee that a startup, even one with hundreds of millions of dollars in funding and a former Intel CEO on its board, can get a fundamentally different and arguably more exotic technology working commercially in anything close to the 4 years between now and its stated 2028 target. There are structural risks specific to XLight as well, beyond the pure physics and engineering challenge. Its strategy depends heavily on ASML's own willingness to eventually adopt or integrate the technology into its machines, since XLight has explicitly chosen not to build competing scanners of its own. That means XLight's ultimate commercial success is, in a very real sense, tied to the cooperation of the very company it is sometimes framed as threatening. There are export control uncertainties given how politically sensitive advanced lithography technology has become. And there is the obvious risk that ASML's own internal research and development teams, sitting on a mountain of institutional knowledge and an existing customer base, could pursue competing improvements to their own light source technology in parallel, potentially neutralizing whatever advantage XLight might otherwise have by the time either technology is actually ready for volume production. Step back from all the individual details, the free electron lasers, the particle accelerators, the $150 million government letters of intent, the quiet talks with Bain Capital, and what you are really looking at is something bigger than one company's fundraising story. You are looking at the first serious, well-capitalized, government-backed attempt in roughly 2 decades to introduce genuine competition into the single most consequential technological choke point of the modern era. Whether XLight ultimately succeeds, gets acquired, gets quietly absorbed into ASML's own supply chain, or fails outright and becomes a footnote in some future retrospective about ambitious semiconductor bets that didn't pan out, the fact that this level of money and talent is now being thrown at the problem tells you something important all on its own. For 20 years, nobody seriously tried to challenge ASML's position because the barriers to entry were so enormous that it barely seemed worth attempting. That era appears to be ending. Artificial intelligence has made the underlying hardware layer, the physical machines and light sources and materials that make advanced chips possible in the first place, suddenly one of the most strategically important and heavily funded corners of the entire technology industry. So, no, there is no quantum machine quietly waiting in a lab somewhere to make ASML obsolete overnight. What actually exists is something almost as strange when you think about it clearly. A former Intel CEO, pushed out of the company he once ran, now betting his reputation on a startup building a shrunk-down particle accelerator to generate light thinner than a strand of DNA, backed by hundreds of millions of dollars from the American government and some of the biggest names in venture capital, aiming to feed that light into the very machines built by the monopoly it is supposedly trying to disrupt. It might fail, It might succeed and quietly become just another supplier inside ASML's own ecosystem. Or it might, if everything goes right over the next several years, mark the beginning of the end of one company's 20-year grip on the most important machine on the planet. Whatever happens, the fact that this bet is even being made at this scale, with this much institutional backing, tells you that the age of ASML's uncontested monopoly is, for the first time in a generation, genuinely being tested. And that alone is a story worth paying attention to.